All right, so let's now get started with the contents of this first lecture. Um, I thought I would start with a short teaser, what you will be able to do after this course. Of course, it's a long journey, but at some point, you will be able to accomplish something really cool with deep learning, with things that you will learn in this class. So, what I was thinking is that these are the total topics that we will be covering in this lecture number one. We'll have a brief course overview, which we are performing right now. Then we'll jump to what is machine learning, the broader categories of machine learning, the supervised learning workflow, necessary machine learning notation and jargon, and then about the practical aspects and tools. So let's just quickly run down to what you will be able to do in the long run. So here are a few examples of what you will be able to do, some cool examples. Um, So, for example, you can convert audio signals into spectrograms, for example, spoken text, and then apply the convolutional neural networks to classify different texts and to extract language out of the audio clips or audio clips. Another example can be working on 3D convolutional networks. So this is a 3D version of the so-called MNIST dataset that you will be seeing a lot in this class, at least during the first introductory lectures later on, because it's a simple data set to get started with neural networks. And yeah, with this project, you can work with FRMI or a magnetic resonance imaging data, so like brain scans and so forth. And yeah, classifying different types of brain scan. So that is another interesting project. And there is another interesting project that you can work on with different types of generative adversarial networks, which will also be covered at the end of this course, where you will be able to generate new data or also mix data from different data sources. So here is a example mixed artistic, um, mixed artistic or paintings or photographs, artistic inputs with portrait of photo models. And then the output was basically here shown on the right, as you can see, like a portrait of person mixed with different styles. These are the styles, and the portrait is mixed with those styles. So this would be an example of style transfer. So just wanted to show you some examples of cool things that you will be able to accomplish at the end of the course. Of course, it is not limited to only these examples. It can be way more elaborated examples or projects that you can work on. So most of the time, people use meta learning or transfer learning. That will also be talking about in detail about transfer learning in this course. But now let's talk about the course or the topics that are planned here. So for this course, it involves lots of topics, as you can see, mainly deep learning and generative adversarial networks, like the course title suggests, and this course is structured into 5 parts. So here are parts 1, 2, and 3 in this slide, and in the next slide, I have some more parts, the remaining two. So the first in the introduction, that's where we are right now. I wanted to give you a brief overview of this course and also introduce machine learning and deep learning. That's what we are going to do now. Then I want to also briefly talk about the history of deep learning, and I think that's interesting because that helps you understand where the things and motivations are coming from. Because yeah, the term deep learning is relatively new. It emerged about 10 to 12 years ago, but it has long history. Deep learning, you can think of it as a fancy term for neural networks, and neural networks have been around for at least 60 to 70 years now. And yeah, some ideas that have emerged very early on that motivated the development of different later on ideas. And we will be covering a lot of things related to neural networks. So in in this or on this lecture, we can think of it as the big picture overview. So we will then just briefly cover the history, and then later we are introducing different topics in this lecture. We will do this step by step and relate that back to the history, and also motivate why we learn about them and why they are useful. And then we will talk about one of the early methods of machine learning, a single layer neural network. So the perceptron algorithm is a very traditional algorithm. Um, Most of you might know what a perceptron is. It's not very commonly used nowadays anymore, but I think this is like an easy going introduction to the problem of classification. So classification things, putting things into different categories, and yeah, I think that will be a good introduction to get started with the topics. And then we will have a small part two here, which is concerned with the mathematical and computational foundations. So with that, I mean like introducing some mathematical necessities like linear algebra. So in deep learning, linear algebra is usually used to express things more compactly. Technically, we can or we could use deep learning without linear algebra, but it would be very hard to write it down and also slow to implement, because when we use deep learning in practice, the computing libraries that we use, they use or they rely on linear algebra. Computational routines that help us executing certain computations more efficiently compared to, let's say, a Python for loop. So linear algebra is like in that way very important for deep learning. We won't be covering or needing any advanced linear algebra concepts, just simple vector dot products and matrix multiplication. That's it, basically. But I think it's still worthwhile covering this in a separate lecture, because laying down the groundwork for the later lectures probably uh, properly makes everything later on a little bit easier. That's what I think. Then we will be talking about a gradient descents. Uh, we will be talking about the gradient descent part. That's a calculus topic. That's gradient descent is the main method for parameterizing or training neural networks. And then after this is more like a refresher. After covering this topic, we will talk about automatic differentiation in PyTorch. So automatic differentiation is calculus as performed in calculus on a computer. You can think of it like that, and we will be using a tool called PyTorch, which is library for linear algebra, automatic differentiation, and then also neural network training or deep learning. And it also allows us to implement things on the GPU to make things more efficient. But for this introductory course, you don't have to necessarily be an expert programmer and user of computers. You should be familiar with certain things on your computer and certain programming aspects. That's all. But we are not here in machine learning engineering, more like giving conceptual overview. And then after the mathematical and computational foundation, we will be talking then finally about neural networks. So in this part 3 here, I will lay the groundwork for your deep learning. So we will talk that what we start with logistic regression, okay, uh, which you can think of as a single layer neural network. So this is basically an extension of the single layer neural network and that we talked about earlier. That is now differentiable. And using the logistic regression as a starter, we will add additional hidden layers, making this a deep network, which is also called multi-layer perceptron. And then we will learn how to train such a multi-layer perceptron using the backpropagation algorithm. Uh, then part three, and then parts here, parts you can see 10 to 12. Um, they are more like tricks for training deep neural networks. For example, regularization techniques to avoid overfitting on your input and normalization and weight initialization. It's just making training neural networks more robust and faster. And then also talking about learning rates and some advanced optimization algorithms. So, like fancier versions of gradients, and you can say, and these are really kind of necessary to make neural networks work well in practice. And then we will go to the interesting parts in this course, or I would say more advanced parts. So these are parts 4 and 5, to be honest. So here in part 4, we will be talking about deep learning for computer vision and language modeling. So we will spend a lot of time on convolutional networks. So this is one big topic. And then we will also talk about recurrent neural networks. They are for language modeling. So convolutional networks are more for image modeling, although you can also use a one-dimensional convolutional network for text, and these will kind of also lay the groundwork for deep generative models that we will be talking about. So in terms of in terms of deep generative models, we will be talking about autoencoders, so-called variational autoencoders. Then we will talk about generative adversarial networks. You may already have heard of them as GANs. So just a long form of writing GANs, generative adversarial networks. Then we will cover some aspects about recurrent neural networks. Okay. Um, uh, for generative modeling, for example, generating new text using in sequence to sequence context. So next in lecture, I will first try to focus only on the prediction parts, but we will also be revisiting this topic for generating new data on text, and then also going into a more advanced topic, adding the so-called attention mechanism to RNNs. And then also explaining self-attention in the context of transformers, which are underlying the models that you have heard about in the media probably. One is called bird of the GPT-2 and GPT-3. So these are building blocks of these models. So we will also talk about those. So don't want to make this too crowded here, but this part will be essentially for images, and so this CNNs will be for images, essentially for images, and these are last two parts will be for text. Okay, we can say these parts can be for images, and this CNN part is also for images, although you can do text transformation as well. But in short, we will focus these parts with respect to images, and these parts for text data as well. So we will have both generative models for images and for text.